New section is entitled Linear Equations. We're going to solve word problems. First type, very popular one. We're going to talk about Newton's law of cooling and warming. Every time, it is not true that every time you cool something or you warm something, it obeys Newton's law of cooling or warming. It's not always true. For many times it is true. And what's the statement of Newton's law of cooling and warming? It goes on to say the rate at which our temperature of a body changes, and it's changing with respect to time. So I'm going to use capital T for the temperature of the body. This here is the rate of change of the temperature of the body with respect to time. And it says it goes on to say the rate at which our temperature of body changes is, that means equal, is proportional to something. I didn't write the something down, but it's going to be K times that. And if that something is very long and complicated, it'll be K times that long and complicated expression. Okay, what is it proportional to? It's proportional to the difference between, there's going to be a difference between the temperature of the body, which we chose to call T, and their ambient temperature. The ambient temperature. That is the temperature of the surrounding medium. Where do you put the object? Do you put it in the freezer? The ambient, or the temperature of the medium would be quite low. 28 degrees Fahrenheit. -5 degrees Celsius. You put it out in the hot sun, might be 100 degrees Fahrenheit. The difference between the temperature and the temperature of the body and the ambient temperature. Let me just write this down a little bit smaller, and we will have the formula. This here, this differential equation is separable. Now, you can memorize this equation, and every time you do a problem involving Newton's law of cooling and warming, you could separate it for every time. But we're going to do it one time, and we're going to formula that's no better or no harder or easier looking than this formula itself. I'm going to move this here to the bottom, and I'm going to move the dt to the top on the other side. And remember, ln of one thing plus ln of another thing is just ln of the product. Now I'm going to integrate both sides. When I integrate the left side, if I call that u, well then that's du on top. That is, I get ln of t minus tm. ln of one thing plus ln of another thing. plus a constant. I can just put that c there. And this equals to the integral of the right side, which is kt. Now, let me make some room up here, please. Now, remember that ln is shorthand notation for log base e. So e to the kt, e to the kt is equal to what I was taking the log of, namely c times t minus tm. I divide the left side by c. I divide the right side by c, excuse me. But dividing by c is the same as multiplying by the reciprocal. That is, it's just a different c. ce to the kt. This is t minus tm. Now all I'm going to do is add tm to both sides. So the right side will just be t, and the left side will be t sub m plus ce to the kt. Now that's the formula, and let me get rid of most of this. And one more thing. The t over the little t is k times t minus tm. These two equations, 1 and 2, are pretty much the same equation. They're pretty much exactly the same. They're equivalent. In fact, let me show you that these two are the same. I'll take the derivative of the left side, get the derivative of capital T with respect to little t. This is a constant, this derivative is 0, plus c times the derivative of that. The derivative of e to any power is e to that power times the derivative of the power, which is k. And I'm not sure why I wrote the plus. Now you may say, well, that doesn't look like number 1 above. You're absolutely right. But based on number 2, ce to the kt, if I bring this to the other side, the right side just has ce to the kt. The left side is t minus tm. But they're equal. We have t is equal to tm plus ce to the kt. If you take away t sub m from both sides, the left side is t minus t sub m. The right side is ce to the kt. And these two horizontal lines tell me whenever I see ce to the kt, like right there, I can write t minus tm, just like I did. So yeah, they really are the same. One is just the derivative while the other one is not. But my advice is to remember number 2. Somebody asks you, what is Newton's law of cooling and warming? You tell them, this is the equation. You tell them that. Now we can do problems now that we know this formula. Now, when we look at the right-hand side, t sub m is a constant, and so is little c, and so is little k. But t is the only unknown. So capital T is a function of little t. So t is tm plus ce to the kt. T of little t if you prefer. Now, let's do a problem. Suppose you heat up a cup of coffee to 100 degrees. Say we do it in steps. Let's list the steps. So you heat up coffee to 100 degrees Fahrenheit. And then place it in a room where the constant temperature is 60 degrees. Well, the temperature of the medium is 60 degrees Fahrenheit. You place the coffee into another room. And then you were told that after 3 minutes, the cup of coffee is 90 degrees. Well, T of 3, that's the temperature of the coffee after 3 minutes, is 90 degrees. And they want to know, when will the coffee, when will it be 70 degrees? So what we do know right away is T sub m is 60. So T is equal to 60 plus C e to the kt. Now, when we say heat up the coffee to 100 degrees and then place it into a room of 60 degrees, that means initially, right from the start of the time, T of 0 is going to be 100 degrees Fahrenheit. So on one hand, using this formula, T of 0 is 60 plus CE to the K times 0. The K times 0 is 0. And e to the 0 is 1. So it's C times this, which is 1. Which is C. C times 1 is C. So we get 60 plus C. That's on one hand what T of 0 equals. But they also told us it's 100. 60 plus what is 140. So C is 40. So update this formula. T is 60 plus 40 e to the kt. Now, I have two choices at this point. I can solve for k, or I can solve for e to the kt. And when I solve for e to the kt, it's okay to just be a function of t. In other words, if I concluded that plus 40 times, if I concluded e to the kt was t to the 9th, well then I can solve for when it's 70. I let this equal 70 and I solve for t. Or maybe I find out that e to the kt is 3 plus t squared all to the 5th power. I can solve this equation in this box because there's only one unknown, t. I can solve it. So I have two options. I can solve for e to the kt in terms of t, that is, I get rid of the k, or I solve for k. Okay, let's see now. We use this, we use that. We have to use t of 3 is 90. Well, on one hand, T of 3 is 60 plus 40 times e to the k times 3, which is the same as 3 times k. And on the other hand, it's 90. So 60 plus this is 90. That's 30. So 40e to the 3k is 30. Divide the left side by 40, you just get e to the 3k. Divide the right side by 40, you get 3/4. The e to the 3k is 3/4. But you know what? This almost looks like e to the kt. What do you multiply 3k by to get kt? Answer. You have the k, but you don't have the t, so I'll put the t in. But that 3's in the way. We'll divide by 3 and the 3 will cancel. That is what you multiply 3k by. What's in this bracket is what you multiply 3k by to get kt. But remember, when you raise to powers, you multiply the powers. So I'm going to raise to the t over 3. And I just said what 3k times t over 3 is. It's kt. And I do the same to the right side. So now I know what e to the kt is, and what it is something that doesn't have k's in it. To the record, it's this. Okay, so now I update this formula. T is 60 plus 40 times e to the kt, which is 3/4 to the t over 3. Now I want to know when t will be 70. That is, I want to solve this equation. I'm going to get rid of almost all of it, and we're going to solve that equation. Hope you realize that these are the three terms, and 70 is equal to 60 plus 10. That's 10. 40 times 3/4 to the t over 3 is 10. You should know 40 times 1/4 is 10. But if you didn't, it's cool, because you can divide by 40, you get 3/4 to the t over 3. Divide the other side by 40, and you get your quarter. Now this is the equation we want to solve. And since the unknown t is in the numerator, is in the exponent, we're going to use logs. I'm going to take the natural log of the left side. And remember, the power can come down, and I take ln of the right side. Now, I just want t. Well, this 3 in the bottom goes on top, and this ln of 3/4 on the top, when I cross the equal sign, goes on the bottom. So t is exactly 3 times ln of 1/4 divided by ln of 3/4. That's exactly what it is. And it turns out that this is approximately 14.46 minutes. Work that out on your calculator. Try another problem. Let's heat something up this time. Suppose you have a piece of metal. So the following problem follows Newton's law of either heating or cooling. Then you come to be told that a piece of metal so our formula, because it's Newton, is T equals T sub m plus CE to the KT. Because it follows Newton's law of either heating or cooling. Once I hear that, that's what I write down. Okay, so a piece of metal whose initial temperature is 20 degrees. That means T of 0 is 20 degrees Celsius. It dropped into a container of boiling water. How long will it take the piece of metal to reach 90 degrees? Well, it's placed into boiling water. That's the medium. So the ambient temperature is boiling, which, if I'm not mistaken, is 100 degrees Celsius. Okay, so let's read it again. A piece of metal whose initial temperature is 20 degrees Celsius it dropped into a container of boiling water. How long will it take the piece of metal? So let's write this down. How long will it take the piece of metal to reach 90 degrees Celsius if the temperature increases 2 degrees in 1 second? That's one question. How long will it take for the metal to reach 98 degrees Celsius? How long will it take the metal to reach 98 degrees Celsius? Okay, so let's look at the first question. How long will it take the piece of metal to reach 90 degrees if it increases 2 degrees every second? Well, it starts off at 20, so it's going to go 20, and 22, and 24, and 26, and 28, and 30. Eventually, it's going to hit the number 90. And what you want to know is how long does that take? Now you can figure out how many 2's you have to add to 20 to get to 90. You can definitely figure out how many 2's you have to add. You have 20 and you want to add 70, which is 2 times 35 to get 90. So I suspect it's going to take 35 seconds. Which actually is very quick. But the problem is, or it's not necessarily a problem, the thing is, the next part, so I wouldn't do it that way because of the next part. The next part is asking, how long will it take to reach 98 degrees? Well, you know what? I would say it's 4 more seconds. I would say it's 4 more seconds. Okay. Now, I did it another way. It doesn't work out that way. So we need to see if what I'm saying is correct, and if not, why not? Well, for example, I also know that t of 1 second later than 0 seconds, it's going to have gone up 2 degrees. So it's going to be 22 degrees Celsius. Okay, so I want to know T equals watt for 90 degrees, and T is equal to watt for 98 degrees Celsius. And I claim it should be 35, and they go from 90 to 98, 4 more seconds. But for some reason, these numbers are going to be wrong. So I didn't have to necessarily use that one. Okay, so what do we know with respect to this equation? We know what Tm is, it's 100. So T is 100 plus c e to the kt. So we use that. And t of 0, on one hand, t of 0 is 100 plus ce to the k times 0. So it's c times this. And k times 0 is 0, and e to the 0 is 1. So this is just 1. And c times 1 is c. So we get 100 plus c. That's what t of 0 equals, 100 plus c. And on the other hand, it equals to 20 degrees. So this must be negative 80. T plus negative 80 is 20. So I would update this formula. Instead of c, or instead of plus c, I'll put negative 20. T is 100. C is negative 80. Minus 80 e to the kt. So now I use this. Now I'm going to use that piece of information. T of 1 on one hand is 100 minus 80 times e to the k times 1, which is just k. And on the other hand, they tell me it's 22. Well, 100 minus what gives you 22? Well, whatever that answer is, that's what e to the k is going to be. And that answer is 78. So coming up here, please, dividing both sides by 80, I get e to the kt is 78. Sorry, I get e to the k is 78 over 80, which is 39 over 40. But this is wonderful. This is just magical. Because if I raise this to the t power, I get e to the kt. And if I raise that to the t power, well, I get that to the t power. E to the kt is this. And this has no k's in it. So I come to this formula right here, and I go that t is equal to 100 minus 80 times e to the kt. 80 times any old way of writing e to the kt. Okay. So now I have my formula. And now I can answer these questions. At what time will the temperature be 90 degrees? So instead of capital T, I put 90. 90 is equal to 100 minus an unknown. But this term is quickly known. It's 10. 100 minus 10 is 90. So 80 times 39 over 40 to the t. This must be 10. Okay, so let me come here and finish, please. Dividing both sides by 80, I get 39 over 40 to the t is 10 over 80. The zeros cancel. I take ln of both sides. Take ln of the left side, I take ln of the right side. But when I take ln of the left side, that power comes in front. T times ln of 39 over 40 is equal to ln of 1/8. Divide by what you don't want. You don't want the ln of 39 over 40, just want t. Do the same to the other side. And this here is your answer. And this fraction is very, very close to 82.13. 82.13 seconds, not 35. So I suspect what I meant to say, actually I got this from her book. What I suspect the author meant to say was, so let me read what the author said. How long will it take the piece of metal to reach 90 degrees Celsius if the temperature increases 2 degrees in 1 second? What it meant to say was, how long will it take the piece of metal to reach 90 degrees Celsius if the temperature increases, 2 degrees in the first second? Not in 1 second, but the first second. So that is why I had it. We knew that t of 0 was 20, so therefore t of 1 had to be 22 degrees. In 1 second, in the first second, it went up, it being a temperature, went up 2 degrees. Okay, now we want to do this whole problem again because we've only done the first part of the question. Now we want to know what t is to get 98 degrees. So the big changes, instead of 90 degrees, we're going to have 98. And this is what we want to solve. All I did, so let's be a little bit more organized about this. This here is our equation, and it just has t's in it, not even constants anymore. It's 100 minus 80 times 39 over 40 to the t. Oh, I want to know when capital T is 98 degrees. So 98 is 100 minus this mess. Well, how much is that mess? 100, 99, 98. 2. Must be 2. This must be 2. So 80 times 39 over 40 to the t must be 2. Because again, these two horizontal lines tell me whenever I see this, I can replace 2. Well, let's see if I'm right. I see it, I'm erasing it, and I'm going to replace it with 2. And then I go, 98 is or equals 100 minus 2. It really is 2. I divide by 80, and now I get 39 over 40 to the t is 2 over 80, which is 1 over 40. And then, since the unknown that we want to solve for is in the exponent, I'm just going to take ln of both sides. And this t, like magic, comes out in front. Dividing both sides by this amount, the left side will just give me t, and the right side will give me ln of 1/40th divided by ln of 39/40th. And that exact answer is fairly close to 145.7 seconds. Now, let's do another type of problem. For growth and decay. We have that the change in x over time is just k times x. That's the formula. dx dt is kx. I'll interchange those two. dx over x is k times dt. Then I integrate. The integral of the left side is ln of x plus ln of c, the constant. That is ln of cx. The right side is k times t. So that understood e down there gives us e to the kt is cx. Dividing the right side by c, I just get x. Dividing the left side by c, or multiplying by c, I get this. This is the formula. For growth and decay problems, that's the formula. But it really needs to be stated this way. You know, some growth can be linear. Some growth can be linear. Every week, the dog grows 1 inch in length. Next week, grows another inch. The next week, it grows another inch. And it keeps doing that. Fair enough. At some point, it stops doing it. But that's not exponential. That's not exponential. Some things can grow linearly. So it really should say something like this. The population of a community is known to increase at a rate proportional to the number of people present at time t. So the population of the community, I'm going to call x, is means equal. Wow. That's not untrue, but here is the equation really. The population, alright, sorry about that. The population of the community is x, and it is known to increase at a rate proportional to the number of people at time t. The population is known to increase at the rate. So the population of the people is known to increase at a rate. This is the rate that the population of the community increases. And it is known to be proportional, that means equals k times the number of people present at time t, which we call x. That's exactly what I have here, and that equation is equivalent to this. So, the population of the community increases at a rate. The population of a community. Now, when it says is known to, we can get rid of that. the population of a community increases, I can only spell increases at a rate. Okay. So I had enough for this writing and drawing on it. The population of a community is known to, I'm not going to write that. The population of a community increases at a rate proportional to the number of people present. Proportional to the number of people present at time t. So let x be the number of people. So proportional to means equals k times. The number of people present at time t is x. And the population of the community increases at a rate. That's the population of the community. And if it increases, that means derivative. So that's how we get this formula. Okay. So I'm going to read it again, and it says the population of the community is known to increase at a rate proportional to the number of people present at time t. Then it goes on to say, if the population doubles after 5 years, then when will the population, and part A is say triple, and part B is quadruple. Triple means becomes 3 times as many, and quadruple is 4 times as many from the beginning. So the question is, how many people are at the beginning? We know x is 0. So here's my formula. I'm going to plug in t0 for t. Is ce to the k times 0, which is c times e to the 0, which is c times 1, which is c. This here is the initial population. Now I know when I plug 5 into this formula, x of 5 on one hand is ce to the k times 5. On the other hand, the population doubles. It used to be c, now it's 2c. Now here's something really cool. I can divide by c. That is, it didn't matter whether c was 1,000,000 at the beginning, or c was 11 people, or c was 1,100, or 18,329. The c's cancel. When it doubles, regardless of how many people were initially, when it doubles, e to the 5k must equal 2. Well, to know when it triples and know when it quadruples, I need either, it doesn't matter which c is, because it's going to triple the same day, going to quadruple at the same time, after the same length of time. I just don't want k. So what I do is, instead of solving for k, I'll get rid of it. I'll get rid of e to the kt. I'll multiply by t over 5, or raise to t over 5, which means I multiply the powers. And I hope that you see the t's canceling, the 5's canceling. So that gives me e to the kt is 2 to the t over 5. So rewriting this equation, x of t is c times, not e to the kt, but 2 to the t over 5. Okay. Now I want to know when it triples. I want to know when c times 2 to the t over 5 triples initial population. That was initial population, and now I triple it. Again, the c's cancel out. I just want to know 2 to the t over 5 equals 3. I want to solve for t. So I'll take ln of the left side, and the t over 5 comes down on the bottom. And yes, that line can go longer. And I take ln of the right side. Now it's just a matter of moving the pieces. I move the 5 across the equal sign to the top, and the ln of 2 to the bottom. And that's what t equals, ln of 2 to the bottom. So t is equal to 5 times ln of 3 over ln of 2. Now, although I like exact answers, and that answer is certainly exact, I have no feel for it. I have no feel for it at all. So you really should use a calculator and get an approximation. That is how long it will take to triple. It's a tripling time. Okay, now we want to know, so that was part A. Part B, we want to know when it quadruples, when it becomes 4 times as much. Well, C is the initial population. Let's remember that. So we want to know when C e to the 5t becomes 4. We want to know when that equals up kt. Maybe I actually needed that. We know that, I don't have the formula in front of me anymore. Great. So you get to see part A again. We know when we plug in 5 for t, we're supposed to get 2c, the 2's cancel. This tells me that e to the 5k, like I said, the c's cancel, is 2. Now, if I raise this to the, well, I don't want the 5, but I do want a t. If I raise it to the t over 5, now I have e to the kt is 2 to the t over 5. So updating this, x is equal to c times 2 to the t over 5. Okay. And the initial population is c. So I want to know when the population, which is c times 2 to the t over 5, will quadruple. Becomes 4 times c. The c's cancel. This is really interesting. Things will quadruple the same time, whether you start off with a little or you start off with a lot. So 2 to the t over 5 is equal to 4. Now you can do logs, but I wouldn't. I would say that 4 is 2 squared. If you raise 2 to different powers, you're gonna get different answers. You multiply 2 by itself, different number of times, you will get different answers. 2 to this power is equal to 2 to that power. The powers have to be equal. The powers have to be equal. Now this is a very, very simple, this equation is very simple to solve. 5 times 2, which is 10, is equal to t. It will take you 10 years to quadruple. 5 years to double, 10 years to quadruple. Okay, let us try one more problem. We're told that the population of our town grows at the rate proportional to the population present at time t. So it's this part and that part and then that part. Well, proportional to means equals k times the population present at time t, and maybe I'll call it p for population. Now, the top one, the population of the town grows at the rate. That's the same as the rate of the population of the town. The rate of the population of the growth in the town. That's the p dt. But we know this. And before I used x's and t's, I said that if dx dt is equal to kx, that's the same as, that's the symbol for the same as, x is c e to the kt. The big difference here, if you look at this and this, the big difference is instead of x, I have p's. So maybe instead of x, I should put p. This is the same as p is equal to c e to the kt. You want to use x's, use x's. If you remember the formula with x's, I personally would certainly use x's. Okay, and it goes on to say what the initial population is. It says the initial population of 500 increases by 15% in 10 years. The initial population of 500 increases by 15% in 10 years. What is the population equal after 30 years? Okay. So we know that P is equal to CE to the KT. Well, let's look at this line in black. The initial population of 500. Well, P of 0 is CE to the K times 0. K times 0 is 0. So it's C times E to the 0. C to the 0 is 1. C times 1 is C. That's what P of 0 equals using the formula. But they told us what it equals. It's 500. Oh, you mean C is 500? Yes. So copying the top equation, except I'll plug in 500 for C. P of T is 500 E to the KT. Now, they told us it increases by 15% in 10 years. So in 10 years, on one hand, we have 500 e to the 10 times k. On the other hand, we have 500 plus 15% more. Or, how I like to do it, you have 1.15 times 500. However you do it, this is 75 plus 500. That is, you should get 575. So this is equal to that. 500 e to the 10k is equal to 575. Now, the reason you just can't plug in 30, and here we know C, the reason you just can't plug in 30 and say the answer is because of k. And you can either replace k with an exact value, or you can get rid of k. I choose to get rid of k. Now, I know 25 goes into this number 2 0 times. But this just has 3 more 25s. So it's going to be 23. I want you to start thinking. It's not rocket science. E to the 10k is 23 over 20. But I don't want 10k as the power. I want kt. So I put in my t, and then I divide by 10. T over 10. What this gives me, well here, the 10s cancel. I just get e to the kt. On the right side, I get 23 over 20 to the t over 10. Okay. So remember, C is 500. So right here, instead of e to the kt, I'm going to erase it, and I'm going to put what I'm allowed to put. I'm going to put times 23 over 20 to the t over 10. And now I have that function with the only unknown being 10. I know all the constants. That is, I can give you an exact answer if you tell me what t is. Oh, t is 30. P of 30 is 500 times 23 over 20 to the 30 over 10, which of course is 3. Saves you a big headache on the calculator to realize the power is just the number 3. It turns out that this is a little bit more than 760. I guess you should say it's 760 people. You really can't have a fraction of a person. This completes the section on word problems for linear equations. Work on it. They're real simple.